We are going to do some mathematics now, but I assure you that I will make it simple so that you can follow step by step for a problem that is very common in electromagnetics, which is Poisson equation. So when I say Poisson equation, we are going to do this in a 2D to make it a little bit more interesting, because so far we have been working only on a one-dimensional finite elements. So let's look at a two-dimensional case. So when I say two-dimensional case, assume that my domain is going to be a circular domain, and it is going to be discretized with some triangles. For the sake of simplicity, I am making it really big. Something of this sort. So the entire domain is going to be discretized. So now for this domain, I am going to solve the Poisson equation and assume that my rho, the volume charge density, here in this case will be the surface charge density in a two-dimensional case, is going to be at the center of this domain. And what I am going to do is I am going to force the value of the potential to be 0 on the boundary of the domain. So my domain is going to be the value omega, and this is going to be my dou of omega, and the potential is going to be 0 in all these places. So this is the starting point. So with this starting point, I am going to take you step by step how to solve this problem. So I have given you the domain geometry, but let us look into the governing equations itself. So what we will have is a set of equations given by the Maxwell equation itself. So what we will have is the curl of E is equal to 0, and the divergence of D, which is equal to divergence of epsilon E, is equal to rho. So for us, the first equation can be satisfied by representing the electric field as, let us say, E is equal to minus gradient of the potential phi. Because we have the vector identity, the curl of the gradient is equal to 0. And now phi is the unknown that we have to calculate. Unknown electric scalar potential. Okay, so with this we have started getting into the Poisson equation, and now we have to also additionally give you certain boundary conditions. So let us write the boundary conditions as follows. So we have two sets of boundary conditions. One is, we say the potential is going to be equal to D on certain boundary elements, which we have represented as for certain gamma 1 of this particular boundary element. Let us say for certain parts we say it is going to be equal to this value. We can also say in a different way, this is the Dirichlet boundary condition. We can also have the Neumann boundary condition, which is going to be given by the normal component of the electric displacement d is equal to certain value, let us say kappa of n. So this is, we are defining the normal component of d, and we know d is given by epsilon e. So this is equal to n epsilon e equal to kappa n, and e can be written as minus of the gradient of the value that we have written. So basically what we have is n e, the gradient should be equal to kappa of n. So I am substituting for this value here, and epsilon is the value of the permittivity. So we are going to call this as, for certain domain gamma 2 that belongs to this is a symbol for belonging to this domain. So let us say this is equal to certain part of the domain value. So what we have done so far is basically assigning the value to the boundaries based on certain boundary conditions. For simplicity, in our case we can also say the value of phi equal to 0 at the boundaries. When we do the simulation we will use that condition, but this is a more general way of looking at the problem. The problem is defined, we have got the governing equations, they are given by this equation here. We have now got also the boundary conditions which are given by this equation. Now we are set in place to run into the finite element formulation based on the theory that we have learnt. Don't be afraid, we are going to go step by step. So what we will do now is we will say the value of phi potential inside a domain. So we say now phi inside an element E is going to be a function of x comma y, where x and y are the x and y coordinates. We are in a 2-dimensional domain, so it is going to be a function of x comma y, and I am going to say it is going to be equal to some value constant a plus b of x plus c of y. So what I have done is, inside each of the triangular element the value of the potential is going to be based on certain number. So this is E, this element will have node 1, node 2 and node 3, and I am saying we are going to have linear triangular elements. So we will have at the point within a particular triangle we will have point 1, which is first degree of freedom, second degree of freedom and third degree of freedom. So we can write the basis functions as the function of the 3 nodal values. So what we are going to have is phi of E of 1 is equal to a plus b x1 plus c x1 cy1 sorry cy1, and similarly we will have phi E of 2 equal to a plus b x2 plus c y2, and phi of E of 3 is equal to a plus b x3 plus c y3, where the value x1 y1, x2 y2 and x3 y3 are the coordinate points of these particular nodes for the particular element E. So now we can write the value of the entire thing, what we have written here, the potential value inside the triangle at each of the nodes as a function of certain constants a, b and c. What we are going to do now is I am going to write the entire thing as a function of a weight multiplied by the basis function. So inside the element I can find any point, any point inside the element, the value can be written as certain element, I have x comma y is equal to, I am going to write it as some weighted sum of I goes from 1 to 3, phi of I which is 1 2 3 multiplied by certain basis function v of I. So this is what I am going to do, I am going to expand this further. So stay with me, it is going to be interesting. If you follow it one by one, you are going to get the logic behind it, and then when you look into the code later on or into any professional software, it will be easy for you to understand the physics behind it. So this is the way we are going to do. So what I did is I said phi of E inside a particular node, any point can be written as sigma I equal to 1 to 3 phi of I v of I. So I can expand this pretty much as this is equal to phi of 1 v of 1. So this is the first element, so I can put as element as E. So plus phi of E of 2 v of 2. So if it is going to be specific for the element, we can always put the element number on the top, plus phi of E of 3 v of E of 3. So since the basis function is going to be same for all the elements, I can probably write it simply as phi of E of I v of 1, so v of 1 plus phi of E of 2 v of 2 plus phi of E of 3 v of 3. I have removed the superscript on the basis functions because it is going to make things easier. So now the value of those basis functions, let us say I inside x comma y is equal to, is going to depend on the geometry itself. So I said 1 2 3. So inside the triangle the basis function is going to have a form 1 by 2 multiplied by a of E multiplied by a of I of E plus b of I of E plus c of I of E. So let us say I keep the E here, so this is the way it looks. So where a of E is equal to the area of the triangle. So what we have done is we have assigned the value of the individual coordinates, and this individual coordinates are going to give us uniquely the value of area and the various other parameters. So the basis functions value is fixed once the geometry is fixed. So that is what we have done here. So let us take this further. So we have got the value of a I of E, b E of I and c E of I. The question is, what are these values? I said the moment the coordinates are fixed, the basis functions are fixed, but we do not know how this to compute this a E of I, b E of I, c E of I. They are nothing but depends on x comma, so this is x1 y1, x2 y2, x3 y3. So inside a triangle they are going to be dependent on the coordinates. So inside a triangle, for example, a1 of E is equal to x2 of E, y3 of E minus x3 of E, y2 of E. So I can take out all the E's out, so I can going to write them simply in terms of a1 is equal to whatever coordinate system. So that will make it look easier. So we have run for A1, so we will write it for A2. So A2 is equal to x3 y1 minus x1 y3, A3 is equal to x1 y2 minus x2 y1. Similarly, we will have 3 equations for B and C. So B is going to be B1 is equal to y2 minus y3, B2 is equal to y3 minus y1, and B3 is equal to y1 minus y2. So you see that there is some sense of symmetry here. When there is 1 here, 1 is missing in the right hand side. When there is 2, 2 is missing on the right hand side, so on and so forth. So similarly, C1 is equal to x3 minus x2, C2 is equal to x1 minus x3, and C3 is equal to x2 minus x1. So let me also write it for A1 in one sheet, so it will be easy for you to get a grasp of it. So this is based on our assumption that the function is going to have a value a plus bx plus cy. So each of the terms will have the dimension that is a multiplication of x and y. So a is a multiplication of x and y, b is a multiplication of x and y's, and c is a multiplication of x and y's. So that's way you can be sure that this is correct. And we can also write, so this is for the a's, this is for the b's, this is for the c's. We can also write the area is equal to 1 by 2 multiplied by b1 c2 minus b2 c1. So this is the way we compute the area of the triangle or area of the element. So in a nutshell, what we have done is, the moment our coordinate systems are fixed, our geometry is discretized, we know the nodes, we know the elements, the value of the basis function is also fixed. If we say we are going for a linear interpolation, then we can accordingly find out what will be the value of the basis functions for each of the elements. So that way we are on a safer ground. So we are going to go now one step further. Remember, I told you in the case of one dimensional problem that you have a point, you have 2 degrees of freedom, and the basis functions are going to go from, in the linear manner, 0 to 1. So let us say this is element, so 0 to 1, so this is element 1. For the element 1, the basis function that will have the main contribution will be this one, and this will be the second basis function. For the particular node, you can decide if this is 0, and you have to assign the value of the basis function particularly for the node. For this particular node, this will be the main basis function because this has the maximum contribution. For this particular node, this is the basis function that has the maximum contribution. So in other words, this will be the v of 0 and this will be v of 1. For the node 0, v of 0 will have the maximum value. So you can write as v of I is equal to 1 if, let us say these are j's, so these are j equal to 0, j equal to 1, the nodal numbers. So equal to 1 when j is equal to I, otherwise it will be 0 for all when j is not equal to I. So this way we can say within a basis, within an element, which of the basis function will have the maximum contribution. In this case, what we have is this basis function is v of 0 will be equal to 1 for the node when j is the same as the I. Likewise we are going to do the same thing for the 2-dimensional case. The 2-dimensional case, our basis function v of I x comma y is equal to 1 when the value I is equal to, let us say the coordinate here are j's, when the I and j are matching. So this is going to be 1, if it is 0 it is going to be when I is not equal to j. So I am at a point where x of j comma y of j, so these are j's and this is I. So which of the basis function will have the maximum contribution can be assigned from this particular property on the basis function. So with that being said, I am going to go forward and we are going to say certain properties about the boundary condition itself. I said phi is equal to sigma I equal to 1 to n for the entire domain. This is going to be phi of I multiplied by v of I, and v are the basis functions. So this I can split them into the one which is inside the boundary and the one which are on the boundary. So this can be written as sigma, so I goes from 1 to let us say n of x, phi of I v of I plus for I goes from 1 to so n of d. So let me use the subscript here, n of, this is the inside the domain and this is on the boundary of the domain, which I have written as n of d is equal to phi of I on the boundaries v of I on the boundaries. So these are the boundary contributions. We can separate them in order for us to do some manipulation. So now what we are going to do is we are going to use this equation into our initial formulation. The initial formulation gave us the value for our partial differential equation for which we have to do some calculation. So I am going to substitute the value for phi using this here and I am going to integrate it over the entire domain. So this is what I am going to do. Let us take it one by one. So what we have got is we have got a value which is the divergence of d, that is equal to divergence of epsilon multiplied by minus gradient of phi equal to rho. This we have. So I can take the minus sign out. What I will have is minus divergence of epsilon gradient of phi equal to rho. So I am going to integrate it along the entire volume. So I am going to integrate it inside the domain and I am going to have the equation with the minus sign out, epsilon equal to so this step is clear. So I said we can do finite element in two ways. We are going to use the weighted residual method and then we can also use the Galerkin approach. The Galerkin approach and the weighted residual method only varies by the changing of the weighting function, making them equal to the basis function. So let us take a simple starting point where we will start with the weighted residual and then we will decide how to go forward. So I am going to multiply this with the weighting function. So what I am going to do is I am going to multiply this integral minus w of I, this is going to be divergence of epsilon is equal to sig. So now this is the starting point. I am going to use the vector identity because here I have got a divergence and the value of the del is on the potential itself. I ideally want to move this divergence on the phi to the weighted function. So that is why I am doing some manipulation. What I am going to do is I am going to use the identity Wi minus epsilon. So this is the vector identity that I am going to use in this particular equation. So I am going to substitute for this value here using the one on the right hand side, and I can apply the Gauss theorem also. The Gauss theorem is basically saying the surface integral divergence of omega I epsilon phi equal to, so when I have a surface integral over that particular surface, it is going to be the boundary of the surface, which I am going to write it as the normal component of the value of the field that we are going to compute. So this is the Gauss's theorem that takes the divergence of a field over a domain is equal to the normal component of that field over the closed boundary of that surface. This particular thing is a volume, this will be a closed surface. If this is a surface, this will be a closed boundary. So what we are going to do now is we are going to use these two formulas onto our governing equations to simplify this, because we wanted to take out the del on the phi outside and then we wanted to put it on the weighting function itself. So this is the manipulation we are going to do. Let us see how the equation itself is getting transformed. So we have epsilon del omega I dot del of phi is equal to the integration over the surface rho times thing plus the closed boundary, what we have talked about, closed boundary, the normal component of the same flux field that we are talking about, times. So what we have done is we have transformed the equation that we have got here. We have applied the vector identity to transform this, and we have used the Gauss's theorem to get to the point where we have the right hand side integral will be represented as the surface integral or the closed boundary integral for that particular equation. So with that, what we can do is we can split this boundary into both the domain boundary, whether it is going to be a Neumann condition or a Dirichlet condition. I am not going to go into the detail of that, but right now we know that we have given the value of the Neumann condition and also the value of the boundary conditions which are given in the initial slides. So they are basically the values that we have taken, and they are given by the values that are here. The value of phi on the Dirichlet boundary condition is like this, the Neumann boundary condition is like this. So the kappa n value is here. So I am going to use the Neumann boundary condition and the Dirichlet boundary condition to reduce this particular formula even further. So what I am going to do is I am going to split this into the right hand side will stay the same. So this particular thing will be here is equal to the first part will also stay the same. So it will have plus I have one part of the boundary will be, let us say, the Dirichlet boundary, which will be n component, the same thing, multiplied by epsilon phi of wi 0 plus there is another boundary, that is the Neumann boundary. It's going to be given by the same equation, but the same equation, this particular term is going to be equal to kappa n. So this value is something that we got from here. We said this value is the value that we are having here, and we are going to substitute for this kappa. So that's what I am going to do here. Kappa of n omega I. So I forgot here. So with this we have come to the point where we can basically write the entire equation in the matrix form. Right now what we have done is this particular side is still having the values for which the Dirichlet boundary condition has to be added. So we have the right hand side which is here. So we can write the entire equation in kind of a matrix form by substituting the values for phi, which are written as the expansion coefficients, and also for the values of the expansion coefficients which we have already seen. So what I am going to do is I am going to transform this equation further into the matrix form, but for that I need to write them in a more manageable form. So what I am going to do is this is going to be equal to, so j equal to 1 to n phi of I integral over the domain epsilon of v of I and dot of v of j over the domain is equal to integral over the domain the rho v of I over this plus the Neumann boundary condition, which is given by sigma d kappa, sorry, Neumann is n, kappa of n v of I over the domain of n and minus sigma j equal to 1 to n d, the Dirichlet boundary condition, which is phi of j of d integral over the domain epsilon del of phi of I phi of j. These are all the Dirichlet weighting functions multiplied by the domain, which is the Dirichlet domain. So what we have done now is we have written the earlier equation, the equation which is here. So it has certain functions. I am going to take the values in such a way that I have applied the weighting functions, and using the weighting functions, so I have used the value vi instead of wi because I have used the Galerkin approach, and by doing that what I have done is I have written the form in a much more easy to manipulate form. This is nothing but sigma of k of I comma j multiplied by phi of j is equal to b of I. So the entire right hand side can be clubbed into 1b. So the phi will be here and the right hand side can be written as k of I of j, and where k of I of j has to be expanded further, that is what we will do now. So where k of I of j is equal to, inside the domain will be epsilon del v I del v j over the domain. So this is the way we compute the case, and b of I is equal to integral over the domain rho of v of I into integrated over the domain plus the Neumann condition which is kappa of n multiplied by v of I integrated over the Neumann boundary minus sigma j equal to 1 to number of points on the Dirichlet boundary multiplied by the potential on the Dirichlet boundary integral multiplied by the weighting function, which is again the basis function here, v of j over the domain of Dirichlet boundary. So what we have got is a kind of an expression form. So this is nothing but k matrix multiplied by the potential vector that we have to compute equal to the B vector. The potential will be a vector, number of rolls will be the number of nodes multiplied by 1. So it will be, let us say the number of unknowns are n, so it will be a n comma 1 matrix, and then this will be also n comma 1 matrix, and you will have a value for the k which will be a n comma n matrix, where n is the number of unknowns in the, or number of points in the domain. So it has been quite a bit of mathematics here, but at least you understand how the entire process is done step by step in order for you to get a sense of if you understand the mathematics or not. We will take it to the next level by showing a small simulation. It is giving you an intuitive understanding of how the potentials are distributed around the domain what we have considered. So we will stop here, I will see you in the next module. Thank you.